To understand the super bomb, we need to talk about a tamper. A tamper is something that's used to contain an explosion so that it can build intensity before it finally breaks out. For instance, in the case of the Boston Marathon bombing, a pressure cooker was used as a tamper. The explosive was ordinary gunpowder. If you just set off a bag of gunpowder, you'd have a great big fire, but no real explosion. But if you confine it within a tamper, like that pressure cooker, then the pressure builds and builds until the pressure cooker bursts, and by that time it's a substantial explosion. The Nagasaki bomb, the implosion-type bomb, had a tamper surrounding the fissionable material in the center. And that tamper was uranium. It wasn't the expensive enriched uranium that was used in the Hiroshima bomb. It was the depleted uranium that was left over, basically all uranium-238. When the first hydrogen bomb, super bomb, fusion bomb was tested, the active material, the secondary active material, was a large thermos bottle full of liquid deuterium, the heavier isotope of hydrogen. If you look at this table, you can see that the hydrogen-hydrogen fusion reaction doesn't yield very much energy, and it takes a lot to get it going. But there are two others which work much better, the deuterium-deuterium fusion reaction and the deuterium-tritium fusion reaction. That's why liquid deuterium was used in the IV mic test rather than liquid hydrogen. It's in a great big thermos bottle surrounded by a tamper, and the tamper is uranium-238. Now, what the physicists didn't realize when they designed this test, and this was not really a bomb, this was an 80-ton monstrosity that took up a whole building, what they didn't realize was that once you get the tritium-deuterium fusion reaction going, you're going to get some very high energy neutrons coming out of that. And the high energy neutrons can initiate fission in uranium-238. And so in a typical super bomb, there are three stages. There's fission in the primary, fusion in the secondary, and then fission again in the tamper around the secondary. As a matter of fact, in most cases, that last stage of fission releases about half the total energy in the bomb. So when they set off IV mic, they weren't expecting what they got. They got a much more energetic explosion than anyone expected. And as a result, it hurt some people and destroyed a lot of buildings. This test was on Enewetak Atoll. Specifically, the test building was on the island of Ulugalab. And at the end of the test, the island of Ulugalab had ceased to exist. The whole thing was vaporized. The total energy release was over 10 megatons, 10 million tons of TNT equivalent, of which about 70% came from fission. That one took place in November of 1952. But that device was not something that was really usable as a weapon with liquid deuterium, for heaven's sake. There was no chance it could be delivered by a bomber, still less a missile. You'd have to put it on a ship and sail the ship into somebody's harbor in order to deliver it. So they went after a second way of producing deuterium-tritium fusion, and that was by creating the tritium in situ. They basically had a very large case of lithium deuteride. Now, I should explain the chemistry here. Hydrogen normally acts like a metal and reacts with nonmetallic things like chlorine or sulfate ions or nitrate ions. But it can also act like the nonmetal in a compound with a metal. And the particular compound we care about here is with lithium. There's a compound called lithium hydride, which has nothing in it but lithium and hydrogen, and it is a true chemical compound. Well, you can make it with lithium and deuterium as easily as you can make it with lithium and hydrogen. So that's why lithium deuteride is the material which was used as the fuel, the fusion fuel, because when neutrons strike lithium-6, they will produce tritium. So then you'll have a tritium-deuterium reaction going on. And this was known to happen with the isotope of lithium called lithium-6. The fuel in Castle Bravo, the second big hydrogen bomb test, was not pure lithium-6. It was a mixture of lithium-6 and lithium-7. And the physicists didn't think that lithium-7 would undergo this reaction. But they were wrong. When lithium-7 is exposed to a lot of high-energy neutrons, it breaks down to lithium-6, and then the lithium-6 reacts, just like the rest of it, to produce tritium. So, as a result, the power, the energy release in the second bomb, Castle Bravo, which took place in March of 1954, was 2.5 times what the physicists were expecting. And it caused a lot of damage, first of all. This test was not on Eniwetok, it was on Bikini again. It caused a lot of damage, and it caused a lot of fallout. And the fallout cloud flew over a Japanese fishing boat and killed a guy and made a lot of other people really sick. This was all unexpected. These tests were not really tests of a weapon design. These were pure experiments in which the people executing them had no idea what was going to happen in reality. The Castle Bravo test paved the way for actual deliverable hydrogen bombs because it was dry fuel. Lithium deuteride is a dry material. It can easily be kept inside a bomb for months or years before the bomb is used, and it will function. And the last test I want to tell you about is a Russian test called the Tsar bomb, Tsar Bomba, the Emperor bomb. This is the most frightening picture I've ever seen. What you see here is the fireball of Tsar Bomba. It's 5 miles across. Anything within that 5 miles would be vaporized and utterly destroyed without a trace. This particular one was dropped from about 40,000 feet and detonated about 12,500 feet above the ground. It extends all the way from the ground up to 25,000 feet. 5 miles across. It's only that small because at the last minute it was scaled down. It was supposed to be a regular fission-fusion-fission bomb of 100 megatons energy release. But Sakharov decided that that would just be too big an explosion, so he substituted a lead tamper for the uranium tamper, meaning that it was a fission-fusion bomb with no final fission stage. And that took it down from 100 megatons to about 50 megatons. But that's not the ultimate. The physicist Robert Server told the story of one time he visited Edward Teller in his lab at Los Alamos, and on his blackboard, Edward Teller had different means of delivering nuclear weapons. They included the usual ones: bombers, rockets, torpedoes, etc. But there was one at the end of the list that he wasn't expecting, and that was backyard. So Server asked Teller what he meant by that. And Teller said, well, if you build a bomb big enough, you don't have to deliver it. You can set it off in your own backyard. And that is the real tragedy of the super bomb. There's no theoretical limit to how big you can make it. You can have two-stage bombs, which is most of the bombs in our arsenal, or three-stage bombs like Tsar Bomba, or the 25 megaton bomb that was in our arsenal for a while. And you can add more stages after that. There is no theoretical limit, because in every case, you've got a bomb, and you can use that bomb as the primary for an even bigger secondary to the biggest bomb you can make, limited only by practical considerations.